Good morning, everyone. I apologize for a lack of videos over the past couple of weeks. I am really buried with um, offensive security exploit development course, as well as I just took on a role as the board of directors for Malware Village and World Cyber Health. So I've been extremely busy. Plus, I went on vacation for 3 weeks. So, so it was a work and vacation. I got a lot done. So now we're going to start jumping back into some basic exploit development. Today we're going to cover a basic vanilla buffer overflow. And this is part of my series that I'll be presenting at DEF CON later this year and other venues as Malware Village gets going here. So first off, I'll show you the binary that we're going to be using here. And this is a simple C program we're going to be exploiting. Here's the vulnerable function. Thankfully, they're named vulnerable functions for us. And as you can see, we have a stir copy here. And stir copy does not do bounds checking, so you can overwrite adjacent memory. So this is a very insecure vulnerable function. So what we're going to do, we're going to exploit this function today with a simple buffer overflow. We've got ASLR turned off, and we also have DEP turned off today as well. And we will slowly build out from here over the next couple weeks, and we will bypass all security functions and have a fucking blast doing it. So let me just close this out. Let me fire up my Jeff, and let's open up the binary and have a look. So first things first, gdb-jeff, and I have a video to show you how to set up Jeff and PETA on your system that you can switch back and forth between. Jeff does things better, I find, but PETA is really good for finding ROP gadgets and stuff. So our binary is called exploit1, and it's right here. Okay, so the first thing we do, disassemble the main function. And as you can see here, here's our vulnerable function. So I want to disassemble that. And just to save myself some typing time here, copy, and let's disassemble the main function. Now I'm looking for the stir copy, which is right here. Okay, so this is what happens if we put a breakpoint here. It will be right before the call to put this onto the memory, into the buffer. So I like putting my breakpoint here. So just B for breakpoint. And let's set up our breakpoint here. So breakpoint 1 is set. So now the first things first, I want to find the size of the buffer. So what I'll do is I have a fancy little program here I made. You can do this with MSF pattern create and pattern offset as well, but I like making my own tools so I understand the process better. So first things first, let's put in 1,000, and here's our random generated payload. So what we will do is put this into the buffer, and where it overwrites the EIP, that will give us the size of our buffer. So let's get into our Jeff here. So now we're going to run. Let me grab the format here. Now this, porting this over to Python 3 has been a major pain in my ass, but I finally got it figured out. There was so much change with concatenation problems and strings and stuff like that. So what we will do is take this here out. Let's put our byte string in right here. Whoops. Let's start over again here. Okay, so what we will do, we'll copy our input here. Let's put this into our byte string right here. Here we go, and let's Let's close it off with a tick here, and everything looks good. So what I've had to do, using a print statement in Python 3 just causes major like Unicode UTF-8 problems and stuff. So I've had to go with import sys.standardout_buffer right to actually get this to work good. And I think this is the main solution. So, okay, so we've reached our breakpoint. We just hit continue. So what I'll do, I'll just hit next instruction, and let's display 136 words from the stack pointer, ESP. And as you can see, this is all our stuff is pushed onto the stack. Now, when I'm fuzzing this buffer to find out the size, all I'm going to do is continue, and then I'm going to check the EIP for what value is in EIP. Once I have the value of EIP, I can then calculate with the offset what my buffer size is. So let's continue. And we come up here to EIP, and you can see this is what's overwriting my EIP right now. So this is the return address. So if we just open up our exploit.c, this return 0 is where we are. Return to libc main, okay? So what happens is the instruction pointer is overwritten with this. And if we just continue here, let me copy this. If we just continue here, we get a segmentation fault. So we crashed the program. So that's a really good sign for us. So what I'll do, I'll go back to my Freya, which is the program I put together with a little tkinter. I do plan on making this a little more sexy in the future, but it works right now. So let's copy the pattern buffer I put in. And the substring to find, we're looking for nkxj. And excuse me. So our buffer size is 268 bytes. So now we can start building out our exploit. So let's get to it. So our program is good and crashed, so we don't need Freya anymore for now. So we'll close that out. So let's get a new word. So let's start keeping track. It's 268 bytes. Okay. So what I'll do now is our buffer size is 268. So our return address we need to overwrite is right next to the EBP, which is overwritten with this 268. So what I'll do now, I'm going to put in an input of 268 A's, and then I'm going to try to overwrite the EIP, which is the return address. Okay, so let's paste this in here, and what I'll do, I'm going to print 268 A's, and then we're going to plus byte string BBBB and close that off. So now what should happen, our full buffer should be filled with A's, and then our return address is going to be B's, okay? So this sort of sets up the exploit for us, because what we're going to do in a simple vanilla buffer overflow like this is we are going to put no operations on the top of the stack. We're going to put our shell code in the center. Then we're going to fill the rest of the buffer with junk, which will be A's. On the EIP return address, we're going to jump to the top of the stack, and then what will happen is it'll go through the NOPs, hit the shell code, and then we'll get system shell. Okay? So let's get into it here. And as you can see, the A's are filled up on the stack right here, but I'll hit next instruction. So now everything is filled up. The stack is filled up. Let's have a look at the stack and see what's happening. So as you can see, here's all our A's here. So what I'm planning on doing and here's our B's right here. So this is the base pointer right here, and this is the return address, return to libc main. The EIP is right here. So we have overwritten the EIP, we have controlled instruction pointer, so now we can take over the system. So what I'll do, I'll put a jump address here, and this here will probably use this address here. The program will hit the return, it will jump back here, we will have a whole bunch of NOPs here, and then our shell code is only a small one, 35 bytes, and I have a lesson on making your own shell code in assembly, and you can check that out on my channel as well. Excuse me. And then once we hit shell, it's game over. Okay, so let's start building out our exploit here. Let's make sure our EIP is overwritten, and as you can see, the EIP is overwritten with B, so we have full control. So now what I'll show you next is our shell code, and this is just a basic binsh shell code that I wrote, and it is 35 bytes. Okay, so I won't make you count it or anything. You'll have to trust me, but this is 35 bytes here. So let's start building out our exploit. So we have 268 bytes. The top of the stack we're going to fill with NUPs. So let's do X90. Then we're going to put our shell code, which is 35 bytes. And then we're going to fill the rest of the buffer with A's. And then a return address is going to be a jump to top of stack. Okay? So now we got to do a little math. Boo math. Math is so important in this stuff. So we have 268 bytes plus the jump. So let's do so 268 minus 35 for the shell code leaves us with 303. So I'm going to say let's do times 200 NOPs. Okay, so let's do 200 NOPs plus 35 shell code, and then let's minus 268 is 33. So let's do 33 A's, and this is just junk to fill the buffer. And then we have our jump address right here. So what I can do, let's have a look at the top of the stack right now. And we're going to display 132 words in hex from this stack pointer, ESP. So up here at the top of the stack, we will find an address and we will jump to that. But we'll do that in the next step here, I think. So let's continue. And we have a segmentation fault. Lovely, that's what we want. So let's get back into crafting our exploit. So this worked, 268 A's and our B's, all that worked. So what we're going to do now off the get-go here is let's put in a NOP, which is a no operation, and I want 200 NOPs. Okay, so that'll put 200 NOPs on. Now we need to put in our shell code. So we need to plus a byte string, and let's copy this wonderful shell code here. And paste that in. Now there's there we go. So now we have our 35 bytes of shell code. Now we need 33 A's. So let's do plus, oops. Let's do plus byte A times 33. And then we'll do plus byte BBBB. Okay, so this has the full exploit. So we have 200 NOPs, and then we have our shell code on the stack, and then we have A's to fill up just the junk to the base pointer, and then on the return address where we're going to put our jump, we have these B's here. And actually, let me just put in big B's here. Um, hmm. Oh, okay, I see the problem here. We got a little issue right here. And there we go. So you're always going to have a little little whoopsies like that. And it takes a little bit of time to get used to it, but you will. Okay, so let's do next instruction. We're at our stir copy right now. And let's do display 132 words of hex from the ESP. Oh, spelt display wrong. Okay, so let's have a look at our stack here. So you can see the 90s here. This is all our NOPs. And then once we get here, this is our shell code. And then our A's fill up the rest of the buffer, just junk. And here's our jump address. So what we need to do now is this jump address needs to come up here. Do not pick the top of the stack because things change in the binary when it's reloaded. So we try to go down a little bit. So this would be the perfect spot for our jump. So let's write that address down. So now the thing is, we need to put this into Little Indian format because that's the way the computer stores it. So that just means backwards. So let's transcribe that. It would be E0, E0, ED, ED, FF, and then BF. So this is how we write this on the stack to get it to work properly, okay? So our full exploit is already ready to go. And if you continue, of course, we're going to get a SIG-SEV and a segmentation fault. Perfect. And as you can see, the EIP has our B's. So now we're going to put our jump address to this. It's going to jump to the top of the stack up here. And it's going to hit these no operations and go down through it quickly because it doesn't have to do anything. And when it hits here, it's game fucking over, and we get shell. So let's do this. Okay. Okay, so all we need to fix right now is our address here. So let's take these B's out. 1, 2, 3, 4. And it's E0, ED, FF, BF. Okay, so everything looks fine. Let's try this. Okay, so let's do next instruction. Display 132 words in hex from the ESP. And let's have a look. So here's all our NOPs. Our NOPs are set. Here's our shell code right up to here. There's our buffer of A's right up to the base pointer. This is the base pointer here. And then we have a jump to BFFFEDE0, which is this address that we jump to right up. Where is it again? DEO. So DEO. So this return address is pointing to this part right here. So what will happen when this program crashes, it's going to hit this address. It's going to jump to the top, go down through these knots really quickly because there's no operation, hit the shell, and take over the system. So let's hit our continue. And boom, here we go. New process is executing new program bin dash, which is a lower it's a lower shell, system shell. So we just got system shell. This is how you do a basic vanilla buffer overflow. And this is what I'm putting together for Malware Village, for DEF CON and a few other cons around the globe. I hope you enjoy. If there's any questions, please ask. And if you can, give this a share so I can keep making these. Yeah, mostly once a week. So I'm going to be putting out these about once a week, also covering 32-bit assembly, which is really important in this line of work. And I shall get chatting to you guys soon. Hope you have a great day. Bye.